Okay, hello and welcome back to the third out of our four major topics, which is fluid flow. In this chapter or section, we'll understand the importance of fluids in food processing, what they are, the types of fluids, and the basic calculations related to the mass and energy balance of flowing fluids in our food systems. So first we'll discuss what fluids are and then the names for the typical components where fluids pass through, their basic properties and specifically viscosity, and then what are Newtonian and non-Newtonian fluids, which may have been covered in part by those of you who took food physics. So simple lang na pag sinabi nating fluid, ibig sabihin hindi siya solid, therefore it could either be a liquid or a gas. But in reality, in food systems, we are usually dealing with liquids. Because aside from the steam used to heat food, wala naman masyadong food tayo na in gas form natin kinokonsume. Maybe yung CO2 sa soft drinks, no? Or yung air in, let's say, ice cream, but that hardly counts. So most of you are familiar with viscosity, usually um, expressed in centipoise. So poise ha, not poa again. So as in wala kang poise, ganon. Um, in food, we can see that the viscosity varies by a very large order of magnitude. So in this case, it's more than 10 to the 6 to be exact. So as a reference, water at room temperature is 1 centipoise. Milk is slightly thicker. And then syrup is already uh, thousands of orders of magnitudes away from that, no? And we can go as thick as peanut butter. Later on, we'll discuss what viscosity is. So sa food processing, the fluid could be the product itself, which is usually either a water-based or oil-based food product or juices, etc. A cleaning agent, in the case of clean-in-place systems, we usually use diluted acids and alkali and other sanitizers. It could also aid in the transport of solids, as you may have seen in other videos wherein fruits are floating down a sort of man-made river in a processing plant, or as a heating media or cooling media, such as the case for steam, hot water, and the cooling brines used to transfer heat away from the foods being cooled and into the refrigeration system, which uses refrigerants, which are also fluids. So if you recall in clean-in-place systems, di ba, para ka lang naghuhugas ng pinggan, pero sobrang laki ng mga pinggan mo. And there are four major elements in the, especially in the removal of soil, in the concentration of the cleaning agent, the time and temperature, contact time and temperature of the solution, and the mechanical force. So yung fluid flow, it has to deal much with this mechanical force wherein ito yung nagde-determine din ng gaano ka-effective yung cleaning kasi no matter how high the concentration, temperature, how long the fluid is in contact, kung wala naman itong mechanical force na from fluid flow, then hindi malilinis yung tangke mo. So fluid flows when you apply force to it, okay? Through either the use of pressure, gravitational flow, such as when you open a dam, frictional forces, thermal effects. Of course, when you heat a food, we know that the molecules move about and these could create convection currents, among other things. Or if you apply electrical charges and the ions in the fluid react to it, and you apply magnetic fields as well, and even Coriolis forces, which are defined as a deflection of moving objects when the motion is described relative to a rotating reference frame, in this case the Earth's rotation. So you might remember seeing this posted by one of the students in the forum on um, food engineering expectation versus reality. So this is actually a diagram for the pasteurization of milk. As you can see, the red line is the product, the fluid product flowing through pipes. And then there's another line for steam. That's the steam that's used to heat the product, although not in contact. So it's over here. And then this is the heating medium. So the heat comes from another fluid that's being heated. Okay. And there's a cold water loop over here and an ice water loop as well in your heat exchanger. So there's what we call regenerative cooling in this case. So if you can see here, the product goes through here. So it starts out cold and then um, as it passes through, um, it heats up and then it cools down. So papasok siya ng hindi pa masyadong mainit, iinitin siya, and then paglabas niya, malamig na siya. So regenerative cooling takes place in this section, okay, wherein the hot milk is being cooled by ice water, cold water, and the relatively cooler temperature milk that's about to be heated. So in this case, yung init ng malamig, pinapalamig na milk, napupunta dun sa pinapainit na milk. Okay. And that's why it's called regenerative. You're reusing the heat na ginamit mo na pangpainit ng gatas para initin naman yung susunod na mga gatas na dumadaloy. Okay, when we're talking about fluids, we usually hear about pipes and ducts. The simple disambiguation is that they're called pipes if they're round, tubular, cylindrical, and ducts if otherwise. No, usually yung ducts yung medyo mga rectangular yung cross-sectional area or what. And usually pipes are for liquids while ducts are for, well, air mostly. No, di ba? Air duct, di ba? Yung mga centralized air conditioning systems and the like. On the other hand, in terms of drainage, you want to avoid open drains for sanitary reasons. So drains are usually covered to a certain extent. They have small holes or even mesh to prevent insect or rodent infiltration. So pipes used to transport fluids, especially food contact pipes, usually have a smoothened surface and made from food grade stainless steel, unless they are only used for heat transfer and are not in direct contact with the food. And then, as we have discussed in your previous accessory topics about passivation or passivity, the formation of the protective metal oxide coating of the surface when exposed to oxygen or air to prevent corrosion. So passivation again is required so that the stainless steel surfaces will last longer, especially when exposed to corrosive substances in the food and food cleaning agents. Okay, so these are the different basic pipeline components that we have. Kailangan natin to kasi when we're gonna do fluid flow calculations, we usually have different pipes and other pipe components, no? So you have, of course, your pipe, usually straight, okay, and made of stainless steel as well. You have your tanks, usually ito yung nag-hold ng liquid food or ng other liquids used in processing. Elbow, parang yung macaroni. So these are pipes that are bent at an angle to change the direction of flow. Okay, usually dahil ganyan yung shape niya, pag fluid flow yan, nagkakause yan ng konting frictional losses. Okay, because it's slowing down the momentum of the fluid. You have valves like this one. Valves, ang purpose nila again is to regulate the flow or open and close the pipe system. So this one here is what we call a butterfly valve. Huwag niyo po akong tanungin kung bakit butterfly, but basically yung nakikita niyo sa gitna, para yung coin, okay? And then when you turn the knob, so the coin turns at an angle. So obviously, pag nakaharap sa inyo yung barya at pag ganun yung flow ng tubig, it blocks the flow. But when you open it at a 90-degree, then uh, roughly free flow yung tubig dun sa gilid niya. There are other types of valves, of course, and each of those may corresponding effect sa fluid flow, frictional losses, etc. So pumps are the ones used to um, provide kinetic energy to the fluid to make it flow, increase its velocity, and make it counteract the effect of gravity, okay, para ma-pump mo pataas yung fluids. And then you have all the other sorts of fittings. Meron naman tong mga tabular values if in case you need to calculate. So for example, if you're gonna make a pipe system, hindi lang yung haba ng total pipe system yung kailangan mo i-consider, but also how many valves, how many pipes, nasan yung pump, etc. etc. Kasi lahat yun may effect din sa total power requirements needed to have a certain flow rate of fluid through your system. So this is a pipe diagram from Singh and Hellman, originally from Toledo's book. As you can see here, these are what we call the nominal sizes. Okay, and depending on the type of pipe, we have the Schedule 40 sanitary and the heat exchanger tube 18 gauge. So usually when we talk about nominal sizes, ito yung binabanggit, and they may or may not correspond to the inner or outer diameter. For example, in heat exchanger tube, the nominal sizes refer to the outer diameters, as well as in sanitary pipes. However, in steel pipes or Schedule 40 pipes, the nominal diameter, as you can see here, for some reason is even less than the internal diameter. So you have to be very careful about this, because when pipe is mentioned to be of nominal size, you have to know what type of pipe it is and look at this table to determine what diameter to use. So typically we are interested in the internal diameter because that is where the fluid flows, and for the purposes of calculating the volumetric flow rate, yun yung mahalaga, no? But sometimes when you're doing heat transfer calculations, you want to take into account the outer diameter as well to be able to compute for the pipe thickness, which is a factor in heat transfer. So first, let's go to some terminologies. When we talk about fluid flow, it just means that you apply force to the fluid, causing it to deform or flow a certain direction. Remember that stress from your physics is force over area, similar to pressure, okay? And there are two types of stress depending on saan siya na direction relative to the surface. So for example, normal stress is force being applied perpendicular to a surface, so also known as pressure, okay? However, when force is applied parallel to a surface, it is known as shear force. So to illustrate that, if I put my palms together and opposing forces siya, okay, then this is normal stress. However, when you are sliding one down and the other up, no, yan yung shear. So if there was, let's say, a piece of clay in between my hands, so sa normal stress, mapipisat siya. Sa shear stress, mag-shear siya, no? Parang mag-cleave siya pag ganun. Okay. So in terms of shear stress and deformation, there are different types of material classifications depending on how they react to the stresses. So if you apply shear stress, for example, to an elastic material, so it deforms proportional to the stress. So pag meron kang rubber band, di ba, you pull it, and the stronger the force ng pag-pull mo, the more na mag-elongate yung rubber band. But if you let go of it, it snaps back to its original shape and size. Of course, there's a limit to this one, no? Kasi pag sobra yung stress mo, magbe-break yung rubber band, or may times naman na kapag through time, lalawlaw na yung parang yung mga garter ng damit nyo, di ba, over time. They stretch permanently. Pero normally, an elastic material would retain its original shape once the stress is removed. So when you have something naman na plastic, yun, kapag hinila mo siya, kung gaano kalakas yung force mo, ganun din kalaki yung deformation niya, hahaba siya or what. Pero pag tinanggal mo na yung stress, yung paghila mo, hindi na siya babalik sa dati. So, parang mga tao din yan, di ba? Merong iba, pag nawala na yung stressor, back to normal. May iba, medyo affected na, okay. And sadly, yung pinaka malala, yung pangatlo, so yung fluid, no, it deforms continuously and proportionately, but it never recovers even when the stress is removed. So that is what makes fluid fluid. For example, um, water the way it is, no, is because there's a constant force being applied to it. It's a gravitational force, and that's why it continues to deform as a puddle if you put it on the floor or you spill it on the floor, and it doesn't really take back whatever shape it has, no? So, continuous yung deformation niya dun sa application ng force, and permanently deformed na siya. And that's why we have liquids as having no definite shape. Although if probably you'd have a glob of liquid in space, di ba, where there is no gravitational pull, of course it would retain a somewhat spherical shape as governed by its surface tension related properties. But that's another story. So just like you may find it hard to find the ideal person, the existence of ideal fluids are also hard to find. Kasi ideally, parang sa physics lang, di ba, meron tayong mga ideal cases like frictionless plane and so on. So sa ideal fluids, ganun din, ideally want them to have no internal friction, so molecules rubbing against each other, the ability to withstand pressure, and hindi siya nag-shear. However, this is far from ideal, okay? And typically fluids cannot meet these criteria. Because those internal forces that resist flow, yun yung tinatawag nating viscosity. So all fluids have viscosity, even air actually. And that is yung air resistance, di ba? So pag nasa vacuum ka, mas madali kang makakagalaw versus pag nasa atmosphere ka na may hangin mabigat. Okay? And one way to look at fluids is to consider them as matter composed of different layers, like a stack of cards. So before we look at that stack of cards thingy, of course, I want to discuss another property of liquid, which is density, or mass per unit volume of matter. In the case of water, it has this peculiarity, no, na yung density niya with respect to temperature ay nag-peak somewhere around positive 4 degrees Celsius, and then it tapers. Although the density differences are very small, no, kasi like this is just a difference of less than 1% within the range ng minus 10 to 20 degrees Celsius. So again, viscosity, we've looked at this in food physics for some of you. I don't know if Physics 70 series also did tackle this to a certain extent, but again, it's usually referred to as resistance to flow or resistant force against movement or the flowing of fluid. when shear stress is applied. So as we know nga, sabi natin, since constant yung gravitational force na nag-contribute ito ng shear stress sa ating fluid, and that is why your fluids flow with the respect to the direction of the ground kapag walang nakaharang sa kanila. Okay, and this viscosity is what causes it to slow down. So if you imagine liquid as a stack of cards, so each of those cards rub against each other and therefore provide a certain level of stopping power and friction, such that when you push along the plane, the stack of cards, the card on the top apparently moves faster kasi lahat sila nag-start naman at the same position, no? Pero parang mas lumayo yung unang card sa taas, tapos yung card sa bottom parang hindi gumalaw at all, no? So yan yung effect ng friction natin or yung viscosity niya. So again, this is just to look at the different forces. So the normal stress could either be tensile or compressive depending on the direction. Tensile is pahila, compressive is pa-compress, parang pinipipi mo. And then shear force is sa magkabilang direction, pero nag-shear ka dun sa plane. So the way to understand viscosity is like this, no? You have here yung parang stack of cards mo, yung uppermost and lower part, okay? Then you apply a force in this direction. The stack of cards has a height z or a distance between the A and B, and there's a constant cross-sectional area over here. And then VA is the relative velocity resulting from the application of that constant force. So the quantity force per unit area, as you can recall, is similar to the units and dimensions for pressure, diba? So you could either imagine this to be a deck of cards situation, or in this case, water flowing inside the pipe, wherein this is the pipe wall, and this, for example, is the center of the pipe. Of course, the other end of the pipe wall would be up here, and since pabilog siya, radially around, no? So the fluid immediately in contact with the pipe wall or the solid has a non-slip condition, therefore it has a velocity of 0, okay? And the surface is stagnant or not moving, excuse me. We could see here na if this is your fluid, there's what we call a velocity gradient, wherein yung part ng liquid na nandun sa pinakagitna ng pipe, sila yung pinakamabilis yung travel, and then pabagal ng pabagal yon until you come to that last molecule sheet directly in contact with the pipe wall where it has a velocity of 0. Okay? So, of course, kapag mas viscous yung isang product, mas malaki yung velocity ng nasa gitna versus yung nasa may dingding, no? The more viscous it is. Okay. Because nga of parang internal friction doon sa molecules ng fluid mo. So the velocity profile is thus the rate of shear, or the change in velocity of the fluid with respect to how far it is from the surface. Okay, so change in velocity over change in your distance. So di ba parang rise over run, parang slope, and when you make a line from that slope, then you would have the velocity profile, which is related to the viscosity. So viscosity thus represents the numerical relationship between the applied shear stress and the shear rate, or how much force over how much the fluid moves. And this is now your velocity profile. No? So Um, you have here your shear stress given by tau, sometimes denoted as sigma, and the shearing rate is the change in velocity over change in distance from the pipe wall. And so nakikita mo, they are related by the mu. And this mu is now your parang pinaka proportionality constant or the viscosity of the substance. Okay, so the unit for the tau or sigma is in pascals. Okay, and we know that this is a unit of pressure, and that pressure has a lot of different units, no, like psi, or usually kilopascal, psi, bar, and so on. So that mu, typically called viscosity, is actually the dynamic viscosity, which is not to be confused with kinematic viscosity. Pero normally, pag unqualified sinabi natin viscosity, that refers to mu or the dynamic viscosity. So if you were to rearrange mu on the other side and then do your balancing of units dimensions, then you would find the SI unit for viscosity to be equal to the Pascal second. Okay, and again, the typical unit that we use is centipoise, again not centipois, and the conversion factor for that is 1 Pascal second is 1000 centipoise. Okay, we should take note that the viscosity of the fluid is affected by the temperature, because as we know, the density changes with temperature of fluid. Okay, so whenever we do viscosity measurements, we should take note of the temperature at which that measurement was taken. And of course, when using very specific equipment, we want to take note of the settings for that equipment. Let's say if it's a viscometer, the spindle number, the RPM, and even when we took the viscosity reading. So on the other hand, kinematic viscosity is simply dynamic viscosity divided by its density. Although we rarely use this, it's good to know now. So ang SI unit niya ay meter squared per second, and they usually use the Stokes, and 1 centistoke is 1 millimeter per second. So beta is just good to know, but we don't use this much in FS 152. Okay, so break muna tayo. You may want to watch this video that's marginally related to fluid flow, but is related to food engineering in many ways. So earlier I showed you a chart of viscosities of different food products. Again, as a rule of thumb, 1 centipoise is the viscosity of water at ambient temperature. And then thick products like honeys and syrups have around close to 10,000 CP, like honey is 88. And generally, the human eye can distinguish viscosity differences at around 110,000 CP. So other than that, parang yung mga kasinlab lang ng tubig, hindi mo na ma-distinguish alin ang mas malabnaw, and yung mga sobrang lapot, parang hindi mo na malalaman visually kung alin ang mas malapot. Of course, this is determined when you pour the product and visually see the difference in the velocity and yung parang tailing ng product na nagpo-form muna siya ng something mahabang goo bago malaglag instead of falling in drops or as a very fluid motion. So again, here are viscosities from Singen-Heldman. First, see that the air has a viscosity in Pascal second of 10 to the minus 5, or 100 times less viscous than water, but it's not zero, still. Olive oil has around 100 times the viscosity of water. And then glass is actually very viscous substance that are for all intents and purposes treated as solids, but generally you'd expect glass to deform over time. Pero how long that time will be, we're looking at thousands of years or maybe even more. Kaya sa lifespan nating mga tao, hindi natin mapapansin yung pag-deform ng isang glass.
Trial version. Trial version.
So we measure this viscosity typically through the use of capillary tubes or a rotational viscometer. I think you've encountered both, either in your chem food physics class or maybe in a food analysis class. So in the capillary tube, what we do here is there is a change in pressure that causes the fluid to flow. Kapag upright siya, then it's gravity, and viscosity is computed as a function of the flow rate and the pressure drop for a tube with a defined radius r. So the viscosity equation here is given by mu equals to pi delta p r raised to the 4 over 8 lv dot, where the v dot is the volumetric flow rate. So, and that volumetric flow rate is defined as the bulb volume over the discharge time. So, in this case, ayan, may bulb ka, may fixed volume yan. And kapag pinuno mo yan, you just wait for the all the contents of that bulb with the fixed volume to go down through the capillary, and you are able to measure the discharge time, and you know, of course, kung ano yung for the radius nitong capillary mo. Okay, and then you can calculate for the pressure drop and the length of the tube to finally get your what do you call this, your viscosity. So the pressure drop is given by the density of the fluid multiplied by the bulb volume, acceleration due to gravity, and the cross-sectional area. So you can try solving this sample problem from Singh and Heldman on your own to provide some practice calculations for the lab. So simply put, using this equation and the givens, okay, you can calculate for the viscosity. So take note that for each run you will calculate a different viscosity value, and of course you can just average that or just see how much the measured viscosities differ per trial. So the Brookfield viscometer we have in the lab is a form of rotational viscometer. And again, how this works is that the viscometer is actually an instrument that can measure force, rotational force or torque, required to turn the cylinder at a certain RPM. So for those of you who have used the viscometer, or rather for those of you who haven't, so how it works is that there is this cylinder that you dip in that fluid na gusto mong i-measure. Okay, so ilulubog mo ito completely. And then you set the viscometer. So yung cylinder or spindle mo, ikaw ang magpipili niyan. Then i-input mo dun sa machine. Let's say I choose spindle number 1. So I screw it in the machine, and then I input in the machine that spindle number 1 is selected. And then pipiliin ko kung ilang RPM ko gustong umikot si viscometer. Okay. And then paikutin ko siya. And then while it rotates, it reads the current amount of torque being used, and then converts that through computation into a viscosity value. So therefore, kapag nag-iiba yung torque, nag-iiba din yung reported viscosity niya. And generally, we take the viscosity reading after a few seconds na paanda rin yung viscometer. Depende sa test protocol natin. Okay, so therefore, how it works is, so the torque is determined by 2 pi r squared length times the sigma. Okay, if we rearrange that for a coaxial, so pag sinabi natin coaxial cylinder rotational viscometer, ito yung parang hollow yung loob niya, therefore meron kang inner and outer radius. Okay, yung single cylinder naman, parang ito, solid yung cylinder mo, so yung pinaka-outer radius lang yung kino-consider. So viscosity therefore is determined by the torque divided by 8 pi nr, which is number of rotations, the length of the cylinder, and the outside radius of the cylinder. So one good way to visualize this is when you're using a rotational viscometer, di ba may resistance yan kapag may motion ka in, let's say air and water are both fluids, okay? And if you've tried cycling in air versus cycling in water, you know that there's a difference because water is more viscous, or simply walking, if you've tried wading in the pool and your feet are completely submerged, may resistance, and you can measure that through your body, di ba, na parang, ay, mas mabigat yung resistance dito sa tubig pag naglalakad ako. So parang ganun lang yung viscometer in a nutshell. But of course, in a cylindrical viscometer, we assume that the cylinder doesn't add a dragging force that could affect the measurement. While it may be true for Newtonian fluids, it's not necessarily true for non-Newtonian fluids. So we have to be careful about the assumption, or in using rotational viscometers for non-Newtonian fluids. So ito yung example ng cylinders na may inner and outer radius, so hollow sila. So similarly, you could try out this sample problem from Singh and Heldman for single cylinder rotational viscometers. So take note that the NR here is in RPM, but if you're gonna look at the units na ginagamit dito, obviously you want to convert this into per second, no? Kasi kung per minute yan, hindi magka-cancel out yung mga units mo. So be careful about that. So make sure that when you write it, yung units ay pinapakita niyong nagka-cancel out, kasi kung numbers lang, magkamali kayo. So again, you want to differentiate between Newtonian and non-Newtonian fluids. When you have a Newtonian fluid, there is an immediate and proportional increase in shear rate when shear stress is applied. So therefore, parang straight line yung kanyang shear stress versus shear rate curve. Ang tanong lang is kung paganon ba siya, okay? And then, as we know, yung viscosity is the slope, di ba? So, generally, those we consider to exhibit Newtonian behavior are waters, vegetable oils, milk, and juices. Yung mga karamihan ng medyo low viscosity nating mga kaibigan. On the other hand, kapag mas complex yung systems, especially yung liquids containing dissolved or suspended solids, non-Newtonian na yung behavior nila. So, maraming klase ng non-Newtonian fluids. Of course, the two major ones are the shear thinning and shear thickening. Okay? In this case, parang hindi straight line yung nagiging graph niya kapag ginraph natin yung shear stress at shear rate. So you can learn and watch this YouTube video on shear thickening, and then this one on shear thinning. So again, for those two, shear thinning or pseudoplastics, ang nangyayari based on the name, as shear rate increases, the viscosity decreases. So pag hinahalo mo siya, lumalabnaw siya. These are also called pseudoplastics. And examples are condensed milk, fruit purees, mayonnaise, and mustard, and vegetable soups. On the other hand, there are shear thickening liquids, wherein viscosity increases with increasing shear rate, such as cornstarch in water. So yung nakita nyo nga na kapag cornstarch in water suspension at a high concentration, pag inapakan mo siya, seemingly solid. So shear thickening liquids have applications outside food, no? Actually, meron nga parang ginawa sila bulletproof vest, no? Kapag pinukpok mo lang ng daliri mo, parang ang lambot niya, ganon. Pero kapag yung instantaneous force ng isang bala na tumatama dun sa object, no, parang bigla siyang magiging super viscous na kaya niyang pigilan yung bala from penetrating. Pero otherwise, hindi naman siya talaga rigid na material. Okay. Then we also have Bingham plastics, which has a yield stress. These are plastics that will only flow if a yield stress is exceeded. So, di ba yung tomato ketchup na pag kahit baliktarin mo yung bote ng ketchup, hindi yan malalaglag kahit mag-flow man lang ng sobrang bagal. Suspended animation siya talaga. Pero pag tinaktak mo ng malakas, pag sakto yung taktak mo dun sa yield stress niya, bigla na lang laglag siya, di ba? So, yun ang Bingham plastics. Alright. So, here are examples of the non-Newtonian. So, if it's Newtonian, ganito siya. Kapag dilatant siya or shear thickening, here's how the curve would look. And pseudoplastic, ganito naman. Okay. Ngayon, kapag nakita natin, pag Bingham plastic siya, yung yield stress niya nandito. So, it will only start to flow if this point is exceeded. However, even among Bingham plastics, you could have mixed types wherein Bingham siya, but also displays shear thickening properties or displays shear thinning properties. So another way to look at this is if the x-axis is the shear rate and the y-axis is your viscosity, a Newtonian fluid would have a consistent viscosity regardless of the shear. So the plastic, magdi-decrease yung viscosity niya with increasing shear rate. The reverse is true for dilatant, magiging viscous siya with increasing shear rate. As you can see here for Bingham plastics, there's a very high initial viscosity until you reach that point ng shear rate na magiging constant yung viscosity niya, and the Herschel-Bulkley, which is a combination of the Bingham plastic and the pseudoplastic. Ganun din, para siyang Bingham plastic na merong pseudoplastic na trend.